on the graph? How would acceleration be represented on the graph? I think you could answer this with probably one word. Slope. You are right. So if you look at the slope of your graph, this would be a description of the acceleration of your car. So another way to think about this is if you've got a velocity graph, which this is a velocity or a speed graph because you just went forward, right? So we're considering speed instead of velocity. But the rate of change of velocity, the rate of change of speed is acceleration. So slope. Number 2, list any time intervals where your acceleration appears to be positive. Okay, list any time intervals where your acceleration appears to be positive. This could be just 2 or 3 intervals, or if you had a lot of ups and downs with your speed, this could be like 7 or 8. So list all intervals where you think your acceleration appears to be positive, and then give a reason. Like, why did you pick those intervals? Acceleration is described by the slope of your graph. Where would acceleration be positive? So I'm just gonna come up with my own graph here, just to illustrate. If I were looking for intervals where my acceleration was positive, I'd be looking at those highlighted intervals. Does that make sense with what you were just looking for? So if acceleration is represented by slope, and I'm looking for positive acceleration, I'd be looking for a positive slope of that speed or velocity graph. Okay. You guys okay with number 1 and 2? Those okay? Okay, we're eventually going to kind of funnel this down into something really important. So number 3 says, draw a line connecting the points representing speed at 6, t equals 6, and t equals 8. And so literally just, get on your graph and estimate the best you can where those would be. So, for me, if if this is 6 and 8 is over here somewhere, I don't know, then I would just put a dot there, I'd put a dot there, and I would attempt to use a straight line. There we go. Hello. Grab a sheet right there. Okay. So then the question is, and I don't know if you know this terminology, I have said it once this year, what kind of a line is that? Say again? Secant. Secant line, yeah. So a line that intersects a curve in the 2 points like that one does, we would call that a secant line. Secant line. And then here's where maybe there's going to have to be a little bit of a thought process here. There is a right answer to this. What does that line represent in terms of your car? The context of this situation. What does that line represent? Average change of speed, I think we could maybe sum it up, average acceleration. So they both used a really key word, and that is average. Right? So this is an average acceleration is what this secant line represents. It does not represent the acceleration at 6 or the acceleration at 8. It just represents an average acceleration between the two. Bailey, you had a question. Awesome. Okay, so I don't know how that worked out for you. I don't know if you had a positive or a negative average acceleration, or you could have even had a 0 average acceleration for that interval. Mine appears to be positive. Okay. Okay, so number 4. You guys okay with number 3? Secant line represents average acceleration. All right, so number 4. again, we're kind of circling around something we'll get to here in a little bit. It says, write a formula for the average acceleration on the time interval from 6 to just some unknown time t. So we just did 6 to 8. We drew in that little secant line. What if I wanted to be a little more general? What if I wanted a formula that would help me have the average acceleration of like 6 to 7 or 6 to 9 or 6 to 10 or 6 to any time that I want? Think about what formula that would look like if I want to know the average acceleration from 6 to whenever. That's okay. That would be a good general way to start. Distance over time. Let's think of a formula where I could plug change in what? Yeah, so it's not really distance over time because this is a velocity graph and I want acceleration. No, so that you're still thinking I think you're treating your graph like it's a position graph and that we're heading for velocity. If I want acceleration, I want to know the change in velocity or change in speed over change in time. Let's try to get even more specific than this if we can. So if I said something like average acceleration would be change in velocity or speed, because in this case it was the same thing, over change in time. How could I be a little more specific? Specifically for the interval from 6 to t. It means the 6 and the t have got to be important. Say again? Okay, so I think I would say probably 6. You could do t minus. Let's do t minus 6. You said t minus 6, right? Yeah, I think it makes sense because t is bigger. Okay, so where would the t minus 6 go? Would that go in the numerator of our fraction or the denominator? We have to go in the denominator. Okay, so if we say t minus 6 down there, what would have to go in the numerator to go with that? V of t minus v of 6. And this formula, you guys are doing great. This formula right here would give us the velocity between 6 and whatever other time we pick. So, if we wanted to pick 10, we just plug a 10 in for both t's, and we'd use our graph perhaps to figure out what v of 10 is and v of 6 is, and we would do a little arithmetic, and we're done, right? Okay, so in terms of the graph, like think about the graph. This average acceleration, let's go back and think about this. This formula is really expressing what aspect of the graph? Slope. We kind of answered this already. This is slope, isn't it? I just want to remind you, this is the slope of the graph. And if you think about it, let's go back to old Algebra 1 stuff when you first learned about m, right? Remember m was equal to delta y over delta x. That was the slope. And if you wanted to expand that out, what was delta y? y2 minus y1 over x2 minus x1. Of course, the y's and x's are just sort of general data points. They're not as specific as our v's and our t's. But I just want you to see it's the same thing, right? This is just the average slope between any 2 points. Are you starting to make a few connections here? Okay, we're headed a little more specific now. Number 5 says, how could you find the acceleration at t equals 6? This is a huge difference. The one word that makes this very different is that word, at. What do you think, Anna? So now we're not talking about a secant line anymore. We're talking about a tangent line because it's at t equals 6. It's not between 6 and some other time. So what could I do? Any ideas on how I could change this from being an average acceleration between 6 and sometime t and kind of narrow it down so that it's just the acceleration at 6? Say again?
I'm going to say find the slope of the tangent line.
And how would you do that? I agree in philosophy. Totally agree.
Would you do sine over cosine?
Sine over cosine is equal to tangent, but when we say tangent line or slope of tangent line, we're using the same word with 2 different contexts. So we're not really talking about like a tangent of an angle. The tangent line is just one of those lines that hits a curve in one point.
Okay.
So we're not going to do sine over cosine. Andy, what do you think?
So let t be infinitely close to 6. And then
So how do we express that?
as t gets
I agree, totally agree with you in principle. I'm looking for a very specific word that would kind of sum up everything you're saying. Just one word. That's a pretty nice word, but if we differentiated what we have up there, that's not really going to do it. There's another word, very calculus-y kind of word. Not derivative. So let me see if I can frame this a little bit better. If this right here is my formula for average acceleration, this would be a better way to frame the question. Listen carefully. If that in that brown box right there, if that's the formula for my average acceleration, what could I do to that to turn it into acceleration at 6? And Andy was describing it. He just didn't use the word that I really wanted him to use. Say again?
You can take out the, like, change, velocity.
Take out.
It would just be like the velocity at 6 over 6.
Okay, sort of, kind of. And you're like sort of doing the same thing Andy did a little bit, I think.
The denominator goes to 0.
Why?
Sunny. It's 6
That's a
Yes.
limit.
Why though? Oh, so somebody just said it. Limit. You need to use a limit. That's right. I was just waiting to hear that word. And that's what Andy, did you hear Andy say as t gets closer and closer and closer to 6? He's talking about the basic idea of what a limit does, right? You get closer and closer and closer to something. Yeah, so that's it. Thank you, Santi. Very good thinking. So if I wanted to know the acceleration, not between 6 and some other time, but as close as I can to just getting acceleration right at 6, I'm going to say, I got to use a limit, and we'll fill in the bottom part of the limit here in a second. I'm going to do the limit of v of t minus v of 6 over t minus 6. I want it to be the limit as what approaches what? T approaches 6. There we go. So the limit as t approaches 6 of v of t minus v of 6 over t minus 6. Interesting, right? So that would basically force, and what Andy kind of said, Bailey was saying it, Anna was saying it, it forces that t to get really close to 6, which forces the denominator towards 0, which means that there's almost no time that's passed by. That tells me I've got my acceleration at 6. Make sense? Okay. Anybody know what this is? It's a derivative. This is actually a version of the definition of the derivative. And we're going to come full circle back around to that here in just a second. It's a little bit different than the definition you probably saw in pre-calc. And that's okay. I'm going to try to open the curtains a little more on your window of calculus and show you there's a little bit more that we could look at. So number 6 is really similar. Based on the good work you guys did with 5, I don't think 6 is going to be too much of a leap. It says write a general formula that could be used to find acceleration at any time a. Any suggestions there? So it's going to be a difference quotient. Specifically, what would that look like? I agree.
F of x minus h.
Oh, what does F mean for velocity, though, or acceleration?
Yes.
We're talking about velocities and accelerations. I have no idea what F of x means.
I definitely don't.
Say again?
V of t minus
V of t minus V of a
over
t minus a. So that right there, what is that? If we just left it at that, is something.
the limit of that.
No. Just leave it at that for a second. What is that? That's average acceleration between a and t, right? Whatever those times are. It's average acceleration between a and t. And then Andy said if we throw the limit, right? So the limit is t approaches a onto that. Now that is the acceleration at any given time a. So if we want to know the acceleration at 3, just put a 3 everywhere you see an a. Then you probably have to use your graph to get some data, and you could run some numbers and come up with that as close as you could estimate with a graph, at least, an acceleration. Okay, so what do you think? Does that make sense? Let me make one more connection for you guys, or help you make a connection. And this is probably what you're familiar with, what you learned last year. Did you guys learn limit as h approaches 0 of f of x plus h minus f of x all divided by h? Sorry, that's not a very good h. There we go. And you were told that thing in red is the derivative. And they're right. So specifically, this would equal f prime of whatever x is. And that's definitely correct. They weren't wrong when they told you that. They were 100% right. They just didn't tell you that there was more ways, a lot more ways this could be expressed. So on the left, that limit as t approaches a of v of t minus v of a over t minus a, that is another version of the definition of the derivative. Is it not? Didn't we use that to find the acceleration of the slope of our graph at one point? We did. So here's the general principle. This, I think, we'll talk about this a lot. But if what you have here is a difference quotient in any form, I don't care what form it is, if it's a difference quotient, if it's something minus something over something minus something, and there's a limit on it, and the limit forces the denominator to 0, that's the derivative. So do you see how it's wide open? It could look all kinds of different ways. For example, what if I told you, you don't have to write this down, you can just look at this. What if I told you that x stood for position of somebody walking around or a car driving around or whatever, and then I told you limit as t approaches a of x of t minus x of a over t minus a. Do you see how that's just a different version of the derivative? If x is position, any ideas on what that full expression would stand for? Not average speed.
The average acceleration at.
Not average acceleration. Maddie, it's not average distance. It's actually not average anything. This full expression right here, that's not average anything. It's at a specific time, something going on at one time.
Show the time action.
Okay.
Position. Does it say time versus distance?
It's essentially a change in position divided by a change in time in that difference quotient. Anybody know what that is? If you haven't had physics, it's going to be hard.
Acceleration.
What is it?
Velocity.
So, well, x of t minus x of a, that is displacement. But it's velocity, as she said first. You're right. It's not just velocity. It's velocity specifically at a point, specifically at t equals a, right? So are you starting to see how, like, the derivative you learned was like a very narrow version of the derivative? There's plenty more. We could look at, we could look at the rate of change, the instantaneous rate of change of sand on a beach, right? As the waves crash in, you guys realize that they pull sand into the ocean? So you could actually look at the derivative of the amount of sand on the beach. That might not look anything like that f of x plus h minus f of x thing, right? And so all I wanted to do here is make this connection to the derivative, because that's what we were really working with the entire time, or like kind of aiming towards. But I also wanted you to realize the derivative can look way different than just that f of x plus h blah, blah, blah thing. It can take on all different shapes and sizes, and we'll do many of them, because it gets more interesting when you do that. That make sense? I hope this was fun. I hope you guys had fun with the car project, and I hope this will give us some good momentum heading in towards what we're going to do right now for the next little bit here. When does class end? 25? 20? 20. Okay, yeah, that'll be pretty good. Okay, so here's the deal. I don't want you to have a mass turn in right now, because I want to transition over to chapter 2. But what I would like to say is, like, I'm looking at these papers here, they all look really good. If you were following and tracking really well, and you had some good thoughts, and you're writing everything down, and you feel like by the time class is over, you just want to turn this in because you feel like, hey, this is done, this is good, totally fine. Just staple or maybe binder clip them all together. Just do that on your way out. Don't do it now because we're going to transition. If, however, if you got distracted or maybe it was sort of messy and you're like, no, he's not going to really be able to see that I actually followed and tracked with this, and you want an extra day, you could just turn it in tomorrow. Or if you're just done, you can get it out of your hands today, that's fine too. Okay? So we'll do that at the end before we get going. Okay, so if you guys would, grab your chapter 2 packet. The very start of the year, we talked about kind of the basic plot of calculus and where we were headed. And I told you that there were two significant problems that calculus deals with. One of them is the area under a curve, the area between an x-axis and a curve, or area between two curves, funky area in other words, and the tangent line problem. Like, how can you develop and figure out and think about what the tangent line is. And so as you can see, we're going to be talking about the tangent line problem and the derivative here. And so let's just take our time here. If it feels like I'm going fast, you just let me know. Some of this you might have heard, maybe some of it you haven't. So here we go. What two things, I'll ask you guys this question like 50 times. And I hope you get it right 50 times. What two things you have to find the equation of a line? Slope and? Not necessarily y-intercept. That's too specific. Just any point that's on the line, right? And of course, that is a point on the line. But you don't need to be that specific. So if I've got a slope and a point on the line, then I can easily figure out what the equation of that line is. Slope and a point on the line. Okay, so what is a tangent line? You maybe have all seen the classic picture of a tangent line. There's going to be another one coming up here in a second. I'll just draw a quick graph. There's your x-axis and your y-axis. Here is some random curve. A tangent line could look like this. I'm going to try to get this to be a straight line. Something like that. The tangent line in and around this point that's on the line is going to only touch the curve in one point. Okay?
So it can't touch 2 points.
So this is where it's a little misleading. So when you define it that way, so like if I did this, check this out. What if let's say I put a tangent line here. Let's say that green point was where I wanted to draw my tangent line. And then I did this. Somebody's going to look at that and be like, well, that's not a tangent line. That hits the curve in 3 points at least, right? It's still a tangent line. So when I say a tangent line hits the curve in 1 point, I'm talking about in the area like right near this point of tangency that we're interested in. So if all you did is you just looked at what's in that circle, you'd say, yeah, okay, sure, it hits the curve in 1 point. There's a little more to it than just that. If you look at the red line right there, sure, like right in that little neighborhood, it hits the curve at 1 point. Yeah, if you extend it, it might hit other points on the graph, but then we're getting away from that point of tangency, and the other things that need to be true wouldn't be true about those other points. And so we're just going to be focusing on that little neighborhood right around that point. Does that make sense? It's a very good question. Okay, so let me get rid of, I don't know, maybe I'll just leave those two. They're both tangent lines. Okay, so to find the equation of the tangent line, we need to have the point of tangency, and we need to have the slope of the tangent line. The point of tangency, slope of tangent line. So I'll just focus on the red line here for a second. The point of tangency is right there. It's where the line and the curve actually do intersect. So that's the point of tangency for the red line. And let's see here. I think I'll say this now. It's not really in your notes. I'll just say this off to the side. At the point of tangency, and I will repeat myself many times because this is really important. At the point of tangency, two things are true. Number one, xy for the line, makes sense? Xy for the line equals xy for the curve. So in other words, at the point of tangency only, the point on the line and the point on the curve are the exact same point. Because they intersect, right? Isn't that what intersection is? The line and the curve are occupying the same location at the same time. Jane, I feel like I've confused you.
No, I'm just,
That's
like X.
that's an L.
Okay.
That's an L. That's a C. That's a C.
Okay.
My one L kind of looked like a 2.
Yeah, I thought that was
Thank you for having a readable look on your face. It's like, I've confused her somehow. Sorry about that. So yeah, I'll say it again. The point on the line and the point on the curve are the exact same thing. Make sense? That's what an intersection point is, right? They're in the same place. And then the other thing that's always true about the point of tangency is slope of the line is equal to slope of the curve. That's a terrible C. There we go. Slope of line equals slope of curve. Now that is true at the point of tangency, and likely that is not true anywhere else. So the point of tangency is pretty darn special, and we're going to use those two truths quite a bit. So the point of the point of tangency is where the slope of the line and slope of the curve are the same, and it's where the location of the line and the location of the curve are exactly the same as well. Doing good? Okay, fantastic. All right, so then this is where we're going to kind of build out this definition of the derivative here. Do you guys do like a million of those definition of the derivative exercises last year? Where you got to like plug in for the f of x plus h, and we're not going to we're not going to do that many of them in here.
That was like the only thing we did.
Yeah. Those are good things, and I'm kind of relying on the fact that you've done a lot of those, but we're not going to do a ton of them here. Okay. Here we go. I like this. So to find the equation of the tangent line, okay, we already said that. There we go. To calculate an average slope, which is the secant line slope, that requires having how many points? 2 points, right? Because that's the secant line intersects a curve in 2 points. But if you're going to be finding the slope of a tangent line, you need to be dealing with how many points? Only one. So here's the classic picture right there in the middle. We got 2 points. There's one of them. There's the other one. C comma f of c, and then the change in between them is represented by this delta x. So does that make sense that if the first point is c, the other one would be c plus whatever the change was? And then f of c, and then the other one is f of the new c, right? C plus the change. And they give you that delta y right there. So let's go down here and let's kind of mess around with this slope of secant. So the slope of a secant line is the slope you learned way back when you were in Algebra 1. So that would be y2 minus y1 over x2 minus x1, or delta y over delta x. And that would be the slope of this blue line that I'm now covering in red. It's the slope of that line. We want to get a little bit more specific. Couldn't we say that y2 is really f of c plus delta x, the bigger, like the further along y? And then couldn't we say that y1 is f of c? Make sense? And then we would say x2 would be c plus delta x minus x1 would just be c. And then can you see how in the denominator the c and the minus c would just add out to be 0? So then what we could do with that, then we could say slope of secant line, I'm just going to continue down here, it would be f of c plus delta x minus f of c all over the result of that denominator, which is just delta x. In your pre-calc class, did you guys ever look at this with delta x's in there, or was it always with h's? H's. So the classic way, the way that you guys saw, you can see down below there, where essentially just the delta x has been replaced with the letter h. What's the reasoning for that? Simpler, right? You just write an h instead of a triangle and an x. They mean the exact same thing. So to add to your menu of derivative formulas, you could have delta x's instead of h's. It means the exact same thing, just different representation. And then, of course, you guys saw this one down here when you were in pre-calc. And so the slope of the tangent line specifically could be represented by that. Although, based on the little 15-minute ride project we just did, you realize the slope of the tangent line could be represented in lots of different ways. This is just the most generic form that we look at. Okay? So let's see here. Any questions on this? I'm assuming you did something like this in pre-calc when you first started talking about, well, what is the derivative? What is the slope of the tangent line? Any questions at all? All right. So I just think I've got a couple more things here, and then I think I'll be done. Yes. Okay. So down here, this note I think is pretty important. The slope of the tangent line, dy dx, often referred to as the derivative, although a derivative could be applied to lots of other stuff. We've already looked at a couple of them: velocity, acceleration, lots of other different ways that this could look. Key terminology here. This is just to save you. I'll be real nice if you tell me, hey, we need to derive that. I won't get mad or anything, but if you do take a calculus class later on, you might have a professor that will like laugh at you and make fun of you and make a laughing stock out of you for calling it deriving. I've actually seen this in person. College professors can just be grumpy sometimes, and they just feel like being mean. Sometimes they're nice. Sometimes they're mean. You just never know what you're going to get. So if you're going to find a derivative, you're not going to be deriving anything. You're going to be differentiating something. Make sense? So differentiation is the effort to find a derivative. That's just terminology. Go flip over to this other page, and this will be good. This will be good here. So go right here. The derivative is, like if somebody looked at your notes and said, hey, you learned about the derivative, what is that? Here would be 3 different ways you could answer that. The derivative is the slope of the tangent line. You could also expand that by saying it's the slope at blank point.
At the point that they intersect.
Yep, and how many points is that? 1. Yeah, slope at 1 point. And of course, that's versus what you learned in algebra, where it was always a slope between 2 points, right? The secant line slope. So the derivative is the slope at 1 point, if you think about it graphically. If you want to think about it in terms of like an application or a contextual situation, then you could say that it's the instantaneous rate of change. And this is a little bit of a misrepresentation. You can't actually find the instantaneous rate of change. You can just get really, 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 really close to it, right? That's what a limit does. Notations for the derivative, a little bit of brief history about this. There were 2 gentlemen back a ways that are credited with this. The first one you've probably heard of. So Newton is generally credited, at least in part, with kind of the foundations of calculus. There was another guy from Germany. Anybody know this guy's name? He's less well known. Okay, so his name was Leibniz. Gottfried Wilhelm Leibniz and Isaac Newton. Leibniz. Leibniz. So Newton's notation started off as y dot. So like for him, y dot meant the derivative of y. And eventually that morphed into y prime. And that's what we use now. So y prime would stand for the first derivative of y. You could also have f prime, g prime, whatever. Those all stand for the first derivative. And since I keep saying first derivative, the natural question might be, is there a second derivative? And yes, there is. So there is a second derivative represented by f double prime or g double prime. And if there's a second derivative, might there be a third? Of course. You could have as many levels of derivatives as your heart desires.
Is it like Roman numerals or is it just lines?
So it's little tick marks, like little apostrophes. But I will say this. If you can imagine, like what if, and believe it or not, there are occasions where it's necessary to find like the 10th or 20th or 40th or 50th derivative. And can you imagine using tick marks to represent the 50th derivative? 1, 2, 3, 4, 5. It's ridiculous, right? So if you were going to do like a 50th derivative, here's how you represent that. It's got to be in parentheses. If there's no parentheses, that means the 50th power of f of x. But if it's f with parentheses 50 of x, that means the 50th derivative of x. So
Would we go that far out?
not in this class. If you take Calc 2, and it's way easier than you think. So it really is. Nobody's going to ever have you say, hey, calculate out the 50th derivative and start at f. There's totally different ways to get around to it, so don't let that scare you off. Leibniz had a different notation, and this is very useful. They're both useful. Leibniz's notation is dy over dx, although we don't often say the over part. We usually just say dy dx. We understand that it really means dy over dx. Is that okay? So dy dx, and can you see the foundations of slope in that? Doesn't it look a lot like delta y over delta x? So Leibniz's idea was like the little tiny d stood for like a little itty bitty change, and whereas delta stands for a bigger change. That's really all it is. So dy dx. So Leibniz came up with that notation, and that is the notation that we use as well today. And if there is a first derivative, according to Leibniz's notation, maybe there's a second and a third and a fourth, right? So a second derivative for Leibniz would be this And later on, we will talk about why there's a squared on the d up top, but there's a squared seemingly on the x on the bottom. So that stands for the second derivative of y with respect to x. And there could be a third or fourth, and you just replace the 2 with a 3 or a 4, or whatever, as you would go up the scale. Make sense? Okay. I think we're going to stop right there for today. So I think I'm good.